Yingshan. I'm a third-year PhD student at Carnegie Mellon University. Research focus lies in understanding language models, especially in terms of how they perform reasoning, generalizing in non-trivial ways, and how they can be interpreted mechanistically. So today I'm going to talk about my recent work. The title is Language Models Need Inductive Biases to Count Inductively. So before we actually dive into the actual content, I'd like to talk a bit about why we study counting. The first reason is that counting is treated as a primitive function in formal frameworks of transformers computation. For example, we have RASP, which is a Python library built for simulating the building blocks of transformer computation. And according to RASP, computing the length of a sequence is a basic operator. Actually, there is another basic operator, which is closely related to length, which is selector width, and it takes as input a predicate function and returns the number of tokens that satisfy the selection criteria. Apart from being a basic operator for formally studying transformer expressivity, counting is also a key component in many complex tasks. For example, modeling counter languages, where one might want to track the depth of brackets in DIC. Or if you want to simulate algorithms, for example, computing the mode in a set or tracking depth of recursive calls. Also, counting is required for deductive reasoning, where you might want to track the number of hops in a reasoning chain. Lastly, even if you simply want to tell your language model to constrain the length of the generation, counting is involved. Actually, this issue, like people recently got interested in this issue because reinforcement learning from human feedback has badly incentivized language models to output lengthier and lengthier outputs. This is because there is a non-trivial correlation between high human ratings and longer paragraphs. So at some point, it would be desirable to develop language models that can count the number of their own generations, count the number of tokens in their own generations, which apparently needs counting. Okay, having that said, let's emphasize why we study inductive counting. The first reason is that inductive counting is related to the interesting topic of length generalization. Length generalization is interesting because constructing out of distribution data via increasing the sequence length is relatively easy, and testing for length generalization helps distinguish learning from memorization. Another reason is that solutions for counting in domain versus counting inductively can be very different from a mechanistic view. Counting in domain can be accomplished by shortcuts, but counting inductively requires a recursive mechanism. In fact, scientists studying how the number sense develops in human kids have revealed that kids learn the first few integers as standalone concepts, while after some point they drastically generalize to the entire integer system through induction once they figure out the association between adjacent integers and they build it up systematically. Okay, now let me clearly define what we mean by counting in this work. We define counting as the ability to map a number word to the cardinality of a set containing the corresponding number of items. The crucial inductive step necessary for generalization should leverage the inductive counting principle, which states that if a word in an ordered number word list refers to sets with cardinality n, then the next word refers to sets with cardinality n+1. Here is an important distinction between numbers in the cardinality context and numbers in the language context. numbers in the language context are treated in the same way as input-output tokens in the vocabulary of a language model. In contrast, numbers in the cardinality context may only appear as internal states, and its exact form may vary across individuals. Okay, there are two fundamental issues that would apparently limit transformers from lens generalizing. So we shall fix them before we actually start the experiments. The first thing is out of distribution positions. So recall that position embeddings are vectors, whether they are learned or fixed, associated with position IDs. So if during testing you're gonna encounter longer sequences, then you will encounter unseen position embeddings. The research community on position embeddings has proposed several remedies to fix this issue. The solutions are essentially augmenting the position IDs such that training on shortened sequences will give you a full coverage of position embedding vectors. The first approach is shifting position IDs. So you don't always starting from numbering the positions from 1. Instead, you could start numbering from a random shift. In that way, the training set will be able to cover the all possible position embeddings. Another thing you can do is through randomized position IDs. So this can be regarded as a more general augmentation. Every time you sample a list of position embeddings and sort them in increasing order, only the order between positions are preserved, but the gaps between consecutive position IDs are different for each input sequence. Randomized position embeddings will also guarantee you the full coverage of position embeddings during training. However, we initially observed worse performance with randomized position embeddings, so we stick with shifted Ps for all of our experiments. The possible explanation is that randomized position embeddings give you unevenly spaced position IDs, so that might harm performance. So here is a list of position embedding schemas that we used. We have absolute position embedding, sinusoidal position embedding, rotary position embedding, scalar position embedding. Now it might need a bit elaboration because it is implemented differently from the additive approach as absolute and the sinusoidal PEs do. So here, token embedding and position embedding share the same stream. So you set aside the last entry of the embedding dimension, and you put a scalar, which is the proportion of the current position to the maximum testing sequence length. And of course, we have the no position embedding setting. So note that all the position embedding schemas take a list of position IDs as input. And since the position shift pre-processes the input position ID, so it is actually independent of which specific position embedding schema to use. So this is actually quite convenient because we can implement this shifted PE to get around the OOD position issue without worrying about compatibility. Okay, the second factor that may break this generalization is out of distribution vocabulary. So basically, you want to train on shorter sequences and test on longer sequences. But for counting, a longer sequence will involve those large numbers, and these are new vocabulary. So the question is, how could you teach the new vocabulary without exposing the model to longer sequences? Let's figure this out step by step. So probably the first thing on the top of your head is we could teach the model to resize the full number list. This is to say we can add additional training examples where the model literally outputs the next integer to the previous integer. This similarly works because it would let the model generate every tokens in the vocabulary during training. But essentially, this is simply flooding the training with lots of bigram statistics. And it is a very bad idea. And our experiments have confirmed that this doesn't work at all. So now you might think we could teach large numbers with a helper token. So that means we use a separate token to teach the model to count towards longer sequences. And this approach actually lowers the barrier of generalization because this is basically saying, I teach you to count banana from 1 to 100, but you have never seen as many as 100 apples. And now can you count apples from 1 to 100? Although this is not exactly what we expect as inductive counting, we still see this experiment as a useful sanity check, because it would be undesirable to establish the counting ability tied to specific objects. Now we propose shifted starts, which is an augmentation technique inspired by shifted positions. So for every input sequence, the first token is a shift value, and the output sequence should start counting from the shifted value +1, the shift value +2, and so on. What's potentially good about the shifted start is that it discourages the model to learn a rigid mapping between positions and output tokens. So it could potentially favor a more generalizing solution. Okay, so here is the list of all our experiment settings. We have the helper token setting, helper token plus shifted start, and the pure shifted start setting. And this is our main results. Firstly, we can see that a helper token indeed makes the task easier. Then we can see that when the vocabulary of large numbers is only exposed by virtue of shifted starts, only a 4-layer rotary position bending transformer generalizes. And the poor performance of those 1-layer and 2-layer models indicates that counting transformers may require a non-trivial computation budget. Okay, so far we have examined input sequences containing homogeneous tokens, but we have also investigated other forms of counting. The first thing is modular counting. It is easier than unbounded counting in terms of there's no out of distribution vocabulary, so we no longer need a helper token or shifted start. Although it seems easier, it could be as powerful as an unbounded counter because if you stack multiple modular counters, it could achieve the functionality of an unbounded counter. We also note that modular counting poses additional challenge for modeling periodicity. The second variant is selective counting. We are interested in selective counting because, firstly, imagine a stack of modular counters. Counters above the first level will have to perform selective modular counting. And in more practical scenarios, tokens that carry useful information are sparse. So that requires selectivity. Generally, selective counting involves a predicate function. Here we simply adopt the identity indicator function as our selection criterion because the additional complexity introduced by a predicate function is orthogonal to the complexity of selective counting. Also note that we avoid out-of-distribution counts because that's the main subject of previous experiments. For selective counting experiments, we construct data with 10 unique tokens. Each token will be seen 0 to 10 times within an input sequence for both training and testing. However, we do have factors that will become out of distribution in testing. These factors are the sum of all counts and the range of dependency in order to perform selection. So here's the summary of the input-output formats for our modular and selective counting variants. For selective plus modular counting, we use a smaller base because we have 10 unique tokens, and we have to ensure that the training set covers the full cycle. So if we use a large base like 10, then it would drastically increase the training sequence length, and that's too expensive. So here's the results. The first observation is that different types of position embeddings are good as different forms of counting. For example, we have sinusoidal and absolute position embeddings doing modular counting. And for selective counting, nope, sign, and absolute position embeddings generalize as well, and also scalar position embeddings. For selective plus modular counting, only the two position embeddings that are good at both selective and modular counting can generalize on selective modular counting. It's interesting to note that actually no position embedding models are quite competitive. This can be possibly explained by the additional opportunities of exploiting shortcuts provided by position IDs, position embeddings. And this definitely requires future study to understand the reason. Another interesting thing to note is the poor performance of rotary position embedding. Initially, we actually expected good performance of rotary because by design, it sort of inherits some periodicity, but I guess it just turned out our thought was wrong. Okay, I guess I can pause here to see if we have questions before I move on to the next part. No? Okay. Okay, let's move on to other architectures. So having talked about all the designs and experiments for transformers, you may wonder how other architectures perform on inductive counting. Let's play around with recurrent architectures. There are three components lying at the heart of a recurrent model. They are reception, transition, and emission. Reception converts the input to the hidden states. Transition updates the hidden state, and emission converts hidden state to output. So for a classic RNN, it implements all these three steps as matrix multiplications followed by nonlinear activations. And LSTM is basically the same, except for some fancy gating mechanism. And recently, there are newer architectures proposed that lies between a classic RNN and dot product attention. Importantly, they strike a better balance between inference time efficiency and training time parallelizability. We have a state space model, which can be written in a form pretty much like RNN with the removal of nonlinear activations. This allows you to rewrite the format into a convolutional form, where you compute kernels out of cascading matrix products. And Mamba introduces input-dependent reception and emission matrices. Lying closer to the attention side, we have linear attention, which seeks to approximate dot product attention without actually computing a dot product. The attention scores in linear attention are modeled by the sum of discounted coefficients that only depend on the keys, not the queries. And with a bit reformatting, a linear attention also admits a recurrent form. And the Rokov model family introduces input-dependent decay factor. Okay, here are the results. The first thing we notice is that an LSTM can easily implement and successfully achieve everything we have asked. However, the newer recurrent architectures have degraded performance. We hypothesize that this is because the newer architectures have reduced expressivity of state transitions because they want to achieve parallelizable training. And that actually comes at a cost. So if you go back to the equations and you pull out those recurrent forms, you can see that for a classic RNN, it has nonlinearity between every state transition. But for state space models, you only have repeated application of matrix products. And for linear attention / Rokov, you don't even have matrix multiplication. You only compute a decay factor. So it's a moving average of history states. Actually, Mario also pointed out a similar issue in his paper, The Illusion of State Space Models, that also calls into question the expressivity of state transitions in those new architectures. Okay, I guess that's everything. So here's the summary of takeaways. If you want to forget about everything I talked about in the previous 20 slides, here are what you want to remember. Counting, in our definition, involves the mapping from numbers in the linguistic context to numbers in the cardinality context. And you should not confuse counting with reciting numbers in ascending order. Transformers require careful designs of the task format and position embeddings to be able to count towards longer sequences. And reinvented RNNs perform worse than traditional RNNs, likely due to their less expressive state transitions. Our work leaves open questions for future investigation. For example, are parallelizable training and expressive state transitions fundamentally at odds? How do limitations in inductive counting carry over to more practical reasoning tasks? And how can we mechanistically interpret why those generalizing models can achieve that? Okay, I think that's the end of the talk. Thank you. And I'm happy to take questions.